Hey guys, how's it going? So last time we talked about measures of central tendency, in particular the mean and median, and so today we're going to be talking about measures of spread. So the median total is kind of where the distribution lied. Measure of spread tells us how spread out is that data in relation to that median or mean. Today in particular we're going to be focusing on the standard deviation. So let's go ahead and just dive on in and talk about the properties of the standard deviation. So a higher standard deviation, which is going to be represented by the letter S, tells you that observations are further away from their corresponding mean. So let's go ahead and just do two quick examples. So let's say this is standard deviation 1 and standard deviation 2. So which one do you think is bigger out of those two, standard deviation 1 or standard deviation 2? And remember, the definition for standard deviation is how spread out the data is, or how far away it is from the corresponding mean. So looking at these two, here's our mean, right? Or our midpoint of our distribution. And now the standard deviation goes ahead and tells us how far away it is. So which one of those two is more spread out? It's going to be standard deviation 2. So standard deviation 2 is actually greater than standard deviation 1. Because standard deviation 1, the data is kind of getting closer and closer to the mean. When we go to standard deviation 2, it's kind of spreading out more and more and more. And so the more spread out the data is, the higher the standard deviation, number-wise, is going to be. It also follows that a standard deviation of 0, so if we're talking about smaller standard deviations, a standard deviation of 0 means that all the observations are equal. Equal to what in particular? They're actually going to be equal to the mean. Right? Because if all of our data is 2, right? So there's a bunch of 2's. The mean is going to be what? 2, right? And if the standard deviation tells you how far away the data is from the mean, if the data is exactly the same as the mean itself, then there is no standard deviation. There isn't any measure of spread. Literally all the numbers fall on that average. So if the mean is being used as a measure of the center for distribution, which the mean, we use that when? We talked about kind of conditions for the mean and median last time, right? So the first thing is that the data is what? Symmetric or skewed? It's going to be symmetric, right? So the data first off has to be symmetric. And then 2, what happens to the mean in particular that doesn't happen to the median? So the mean, if there are outliers, it gets pulled by it, right? So ideally use the mean when there aren't any outliers so that it's not just pulled towards one end or the other. So when we use the mean as a measure of center for a distribution, the corresponding measure of spread is going to be the standard deviation, or again, S, right? So the best situation to use the standard deviation is when the distribution is symmetric with no outliers. So we kind of just talked about that right up here. Right? So no outliers, symmetric, we're good to go. So now we talked about the properties. Let's go ahead and try to find out how we can solve for the standard deviation given a data set. So here you see two kind of scary looking equations, but we'll break them down simply. And actually the one I'm going to be using is the one on the right. And I'm going to go ahead and talk about this point right here. The reason for that is because the version on the right is easier for higher sample sizes and just easier in general, to be honest. So I like to use this one up here. If you want to practice using both, feel free to do that. And you can also check to make sure that both will give you the proper answer. Actually, both correspond. So here on the left, we have this big sigma. What does sigma mean again? Sigma means to add, right? So what are we adding? We're adding, and let's go ahead and just talk this through real quick, and then we'll talk about the steps. So you see how there's xi minus x bar. What is xi? Xi is actually, I wrote it down here, is each individual observation. What is x bar? X bar we talked about last time. So x bar is actually the sample mean. Right? We saw it last time when we were talking about measures of center. So what do we do from there? What this formula is basically telling us, or at least from the sigma on, is saying for each individual observation, subtract the mean, right? That's all in parentheses. So we do that first, and then what happens next? Once we're done with the parentheses, we square every individual observation minus the mean, right? So we square them each, and then at the end, above everything else, we do the sigma. So we end up adding all of these things together. So what we want to do then is step 1, create a column with data, with all the data. So we're going to say xi, each individual observation, all the data, right? So you're going to write down all the little pieces. Next, create another column with every xi minus the x bar. So every xi, every xi minus the x bar. And we do that for each individual observation, right? Because each individual observation minus the mean, we have to do that for every row. The next one is create a final column where we square that. So once we have this second column, we literally square every value across. And the last step is to add up that final column. Now this number here that we end up getting corresponds to this whole term. Does that make sense? So every xi, subtract the mean, square that, and add everything up. So that's kind of like the easiest and most systematic way for us to do that. And we still end up getting that number there. So once we get that, we just multiply that by 1 over n minus 1, which n is what again? So n is our sample size, right? So once we get our sigma and all that craziness done, it's just multiply by 1 over n minus 1, and then just square root everything. That is version left. So let's do version right. I find that one a little easier. Whichever one works for you is honestly your preference. I don't really care. And it also depends on, I guess, how your teacher teaches it or what's in your book. But this one here is an easier version because we don't have to actually do as much work. So what we're doing is, you see here the sigma on the left is telling us that we add up every individual observation, but when it's squared. So we square every individual observation, then add them up. Now the one on the right, where it's sigma xi in parentheses, is add up all the individual observations, then square that number. Does that make sense? So step 1, create a column with all the data. Cool story. Kind of saw that already in the other one, right? Next, create another column with every xi squared. So we square every one of these. Step 3, add up the values in the first column. Step 4, add up the values in the last column, the second one. Cool? So even then, just in describing it seems a lot easier. But now, what are these two numbers representing? So once we get these two numbers, sigma xi squared is actually this one, right? And then sigma xi, then square all that, is actually this number here. And what I mean by these numbers, it's this one, and then just the one in parentheses, right? Because at the end of the day, even though we add up all the individual observations, what do we have to do at the end? Square everything, right? Because it's in the parentheses. Cool, we did that. Square it at the end. Now, and then once we do that, we just plug all the information in. Again, n is our sample size, times 1 over n minus 1, square root above everything else. Now, one last point I want to make is the variance is another measure not as commonly used, but can be found by literally just s squared. It is the standard deviation squared. Now, why don't we use it? The reason we don't use it is because, for example, the units of the mean, let's say, was 4 feet, right? The variance would have units of, let's say it was 4 also. So it was 4 feet. The units would be squared. So we can't really do anything operationally. So math-wise, we can't really add up these terms because feet doesn't add up with feet squared. So what do? We take the square root and use the standard deviation. That's why it's the most commonly used. Because then we get standard deviation is 2 feet, and these two we can use to add up, subtract, things like that. We can do mathematical operations to these without any issues in terms of feet versus feet squared. That's probably a little more of elaborate of a discussion than is necessary, but I want you guys to kind of know why do people use this the variance versus, the standard deviation versus the variance. But they're both still measures of spread. Cool. So let's determine the mean and standard deviation of the following data set. So in order to get the mean, we have to add up everything, right? So we saw that last time. We add up everything and do what? We divide it by our sample size, right? So once we divide by our sample size, we have the mean. So let's go ahead and start off with our column, xi. Xi is 4, 5, 5, 6, 4, 3, 3, 2. So we can add everything up, right? And once we add everything up, we get 32. Don't believe me? Feel free to try it. We're just saving time by having these answers ahead of time. So our sum of everything is 32. So how do we get the mean? We're going to divide that by our sample size, right? But let's hold off on that and let's draw all our columns first and then move towards calculating things. So what's our next column that we'd create in the easier version of our equation? So step 1 was to write all the data down. Step 2 is to create a column with every observation, squared, right? So let's go ahead and square every observation. So we got 16. 5 squared is 25, 5 squared is 25, 6 squared is 36, 16, 9, 9, 4. Once we add that up, we end up getting 140. Alrighty. So now can we calculate the mean? Yes or no? We actually can. So our mean is 1 over n sigma xi. What's sigma xi? Do we have that yet? So do we have sigma xi? We actually do. And it's actually the 32 here. Because what we did was add up each individual observation, right? So we just plug that bad boy right there. What's our n in this case? Our n is our sample size, and we have a total of 1, 2, 3, 4, 5, 6, 7, 8. We have 8 observations. So we're good to go, right? Just plug everything in. So it's 1 over 8 times 32, which gives us 4. So the mean or the average or midpoint of this distribution is 4. What's next? Our standard deviation, right? Standard deviation is square root of 1 over n minus 1 times sigma xi squared minus sigma x squared over n. Put that all in parentheses at the end. So now, which summation corresponds to which sum? So we know that sigma x, or sigma xi, I'm sorry, I forgot to put the little I, is that number in the middle, right? In the parentheses. So we added up all the numbers, that's our sigma xi. What about the other one? This 140 corresponds to sigma I xi squared. And our n we know is 8 still, right? So let's just go ahead and plug everything in. So it's 1 over 8 minus 1 times sigma xi squared, which was 140, minus 32 squared over our sample size was 8. Once we do all that crazy math, we end up with a standard deviation of So we end up with a standard deviation of 1.31. And I'm rounding to two decimal places, just because I feel like it. You know, it doesn't really matter as long as you have around the correct estimation. I like to just do 2 decimal places as my tradition, or my convention. I'm sorry. So let's go ahead and move on to example 2. So example 2, we have the mean and standard deviation again. So why don't we just go ahead and do the same process, right? So our mean is add everything up, divide by n. And to get the standard deviation, we have to have an xi squared column as well. So 1, 1, 2, 4, 4, 6, 7, 7. Add all that up, and we get 32. Crazy, we got the same number. And then our xi squared, we get 1 squared is 1, 1 squared is 1, 2 squared is 4, 16, 16, 36, 49, 49. And so our sum of xi squared is going to be 172. So now how do we get our x bar? It's 1 over, how many observations do we have? A total of 8, right? So 1 over 8 times, and what was our sum of xi? That ends up being the 32, right? Add up each individual observation. Whoops, sorry about that. So add up each individual observation. We get a mean of 4. So we're actually centered around the same thing for both of these. But now, let's see what happens to the standard deviation. Even though we have the same midpoint, maybe these two distributions are a little more spread out than the other. So S is square root of 1 over n minus 1. So it's 1 over 8 minus 1 times, what's our sigma xi squared? Right? So I'm referring back to this equation here. I'm not going to write it again just to save space and time. Sigma xi squared was square everything and then add it up, right? AKA 172. Minus sigma xi again is 32 squared over our sample size of 8. Once you do the math, you end up getting 2.51. Cool, so we have the same midpoint, different standard deviation. That's cool. So let's go ahead and look at comparing both of these. So which of the previous 2 examples, and let me go ahead and remove myself so you can read the full question. So which of these 2 examples, example 1 or 2, are more appropriately described by the standard deviation? So appropriateness for the standard deviation is given by whether, number 1, it's symmetric, right? And number 2, are there any outliers? Now, is there any reason for us to assume that these 2 data sets are not symmetric? No, right? I mean, we have the one on the left is centered around 4. We have 3, 3, 5, 6, and 2. So they're basically kind of spread out. The only difference is that example 2 has a wider range of numbers, but it's still pretty evenly distributed, right? Because we have 1, 1, 2, the 4s are in the middle, and then 6, 7, 7, right? So both these distributions actually look like this. Actually, let me go ahead and draw these. So we have one that's really skinny. And I'm going to do the other one in blue. Blue and a dotted line. So I know it's a little exaggerated, but essentially this is kind of what's happening. We have one midpoint there at 4, and this one is also at a midpoint of 4, right? But what happens is that the data is spread out more on one than the other. So, is one actually more appropriate than the other? Not really, because they're both symmetric, and there are no extreme outliers for either of them. So they're equally appropriate. What's the only difference between these 2 then? All it really is that one of the standard deviations is bigger than the other, right? Which one's bigger, standard deviation from example 1 or standard deviation from example 2? Example 2, right? So that means it's more spread out, which we saw in that little drawing right there. Cool. So we saw the standard deviation, how we apply it, how we use that information to kind of compare distributions, right? Because that's kind of our whole purpose. We have one distribution that's great, but it's also great to know how does one relate to the other? Not only in terms of the mean, so how far apart are these distributions, but also how spread out they are compared to each other, right? So we'll go ahead and move on to our next form of measure of spread. So until next time, thank you guys for joining.